This is the final video in this series on general relativity, and in the last one, number 19, we used what we learned in all of the earlier videos about the mathematics of the geometry of space and time, as well as some ideas about mass, energy and momentum from Newton's theories, to describe a simplified way of formulating Einstein's field equations. Hopefully then, this statement here could be, dare I say it, understood, at least in the sense that we'd gone through enough of the mathematics to see more or less what each term means, why it's there, and what it does. This one-line mathematical statement is really a set of 16 equations for four-dimensional space-time, and at one level they describe the way in which matter and energy distort space-time, and then the way in which that distortion requires the use of a measuring system or metric, which produces measurements which suggest a change in the movement of matter, or as John Wheeler is reported to put this argument the other way round, space-time tells matter how to move, matter tells space-time how to curve. However, these equations, rather than being written like this, are often seen in this form, where they apply, with approximations, to the whole of the universe. As you can see, they have this extra term present, a constant lambda times the metric tensor g mu nu. This constant lambda is known as the cosmological constant. But why is it there? Einstein put it into his equations for one reason, but now, in the 21st century, it's there for a somewhat different reason. And in order to explain this clearly and to do the topic justice, we would really need another fairly lengthy series of videos on cosmology, which would discuss the way in which we might apply the bare Einstein equations to the universe as a whole, to the cosmos, rather than simply to a limited region of space around a mass or whatever. We would also, of course, have to include all types of mass and energy within the universe. It wouldn't simply be a case of thinking about the various masses present in galaxies. We'd need to think about energy, all sorts of energy, momentum, and even what can be called the pressure of the moving material in the universe, the kind of things we talked about when we discussed the stress-energy-momentum tensor in video number 18. In what follows, we shall try to cover the basic ideas of all this, but inevitably will not give rigorous explanations or cover most of the fascinating ground that would be covered in a decent course on cosmology. It will try, as best we can, to explain the reason for the presence of the cosmological constant in Einstein's equations. Before we tackle any of that, it might be good to spend a few moments thinking about some simple Newtonian ideas with regard to the expansion, or otherwise, of the universe, as these ideas will be helpful later when we're thinking about the cosmological constant. As has probably been mentioned before in these videos, when Einstein introduced his general theory, the accepted view amongst renowned astronomers, or perhaps I should say cosmologists, was that the universe was definitely static, neither expanding nor contracting, but just evolving. We can illustrate that belief fairly crudely in the following way. There are no units shown on these axes, and this green line is meant to represent what was believed at the time to be what we might call the relative size of the universe as time passed. Relative to what, you might ask? Well, relative to what it is now might be the best answer. In Einstein's day, the early 20th century, there were believed to be no changes in the size or the general makeup of the universe over time, and so the graph here shows a simple horizontal straight line. The relative size at the current time, now, has been put equal to 1, and the graph is simply saying that the suggested model of the universe was such that its size relative to now was, and always will be, 1. However, assuming the universe is not infinite and never-ending in space, you don't need to think very deeply about gravitation to see that there are fairly basic arguments that can be made against that idea, even if you know nothing of the so-called Big Bang. Even thinking in terms of Newtonian gravitation, it seems fairly obvious that a finite universe, containing as it does massive objects scattered throughout it, must be being pulled together by the force of gravity. Even if for some reason the universe was somehow static at some particular point in time, it must surely start shrinking smaller and smaller eventually. The same kind of argument can be made if you assume that the universe had had some sort of beginning, if it started off by expanding for some reason. In that kind of scenario, we could still say that such an expansion must surely slow down on account of the gravitational attraction. In fact, in Newtonian terms, we can think of there being at least 3 distinct possibilities for the expansion of the universe scenario. And a good analogy for thinking about those 3 possibilities is the idea of escape velocity. As we discussed in video number 1, the escape velocity of an object on the Earth, assuming no air resistance, is given by square root of 2gm over r, where capital M is the mass and capital R the radius of the Earth. If an object is thrown upwards from the surface of the Earth at a velocity less than the escape velocity, it will slow down, instantaneously stop, and then return to Earth. On the other hand, if it starts off with a velocity exactly equal to the escape velocity, then it will escape from the Earth and it will tend towards having zero velocity as the distance away tends to infinity. In other words, it will slow down and never actually stop except at infinity. Thirdly, of course, if it leaves the Earth with surplus velocity over and above the escape velocity, then it will also escape from the Earth, but it will tend towards having that constant surplus velocity as it approaches infinity. And something like these 3 Newtonian scenarios can be imagined to apply to the universe as a whole, and can be illustrated on a plot of the relative size of the universe against time on the same axes that we had a moment ago, where, once again, note there are no units shown. Crudely then, this blue curve would represent a universe which started off with zero size, but was expanding from the get-go. Gravity slows it down to stop here at the top of the curve, where it would have a maximum size, and instantaneously it would have zero velocity of expansion, after which time the universe would contract right the way back to zero size. This point could represent the now situation. This curve illustrates what we might call the Big Bang and also the Big Crunch. This blue curve, however, is just one possibility. It's analogous to being below the escape velocity in the earlier illustration involving a single object moving away from the Earth. However, what if the universe was expanding in such a way that things were a bit like an object starting with exactly the escape velocity from the Earth? This second purple or mauve curve represents a situation where the expansion of the universe is what we might call just right, in the sense that the velocities of expansion tend towards zero at infinity. Again, this point, say, could represent the now situation. This means that the universe may have started from zero size at a different time in the past on this diagram, but it is expanding from that Big Bang and it will continue to expand in the future, getting slower and slower until everything is so far away from everything else that there would essentially be no inward pull, and the velocity between things would be all but zero, becoming equal to zero at infinity. That means that this purple or mauve curve would be asymptotic to a horizontal line on this graph. The third possible scenario, from this simplistic way of thinking of the mass of the universe pulling things inwards, would look like this red curve, where things start off at the Big Bang with even higher velocities, analogous to an object leaving the Earth with a velocity greater than the escape velocity. Once again, the now time could be here, and we can see the start of things back here, after which the universe continues to expand, not slowing down to zero velocity, but rather ending up with everything moving apart from one another with some kind of constant velocity. this red graph would be asymptotic to a straight line of finite gradient. Eventually everything would be so far away from everything else that there would effectively be no slowing down from any force of attraction, and the universe would continue to increase in size and separation at a constant rate. Here are those three possible scenarios on the same graph, with a suggested now position marked at the same time. Now this might be said to be a rather simplistic Newtonian view of the possibilities for our universe, and perhaps Einstein felt that using his new and more sophisticated theory of gravitation, his new set of 16 equations, he could perhaps show that they could describe a model of the universe which was indeed static, thus improving on the Newtonian idea. However, the first attempts in 1917 at modelling the universe using Einstein's equations also predicted a universe which was being pulled together, slowing down or contracting. We'll see in a moment how these bare equations of Einstein still predict a kind of pulling in effect on the universe, and that in turn will imply that it can't be static. And so if cosmologists insisted that it was static, there would be a need to add something to these equations in order to make them describe such a static universe. And that's what we'll now discuss. Our starting point, of course, is to find out how on earth we can apply these equations to the whole of the universe in one go. These bare Einstein equations, the ones without the cosmological constant, are coupled non-linear second-order partial differential equations, and they contain information about every point or event in space-time. How can you say, for example, that you know the 16 g mu nu values or the 16 t mu nu values at every point in the universe, and then write down the 16 equations for the universe? You can't. These are continuous equations. How can they possibly be made to apply to something so lumpy as the universe? Clearly, if we want to try and apply them to the whole universe in one go, and see what the cosmological constant's all about, we will need to make some fairly drastic assumptions and simplifications about the universe. And the two main assumptions that are usually made are that the universe can be taken to be homogeneous and isotropic. What we mean by these two terms is that on a large enough scale, the universe can be taken to be uniform throughout, and that it looks the same in all directions. And the key to accepting these assumptions is the phrase, on a large enough scale. We ignore totally the possibility that any local parts of space can be inhomogeneous or irregular. And perhaps the following illustration will help a little to see the meaning of the words homogeneous and isotropic in this context, and also help to appreciate the phrase, on a large enough scale. Suppose we had a large container full of air, containing oxygen molecules, nitrogen molecules, and other molecules. We could depict it like this, where just the oxygen and nitrogen molecules are illustrated in roughly a 4:1 ratio. The spacing of the molecules here bears no resemblance to reality. The air is in a container which is at rest, but obviously the molecules themselves will be moving relative to one another. But let's say they're moving slowly. In other words, it's very cold. We could class this as what is known in fluid mechanics as a perfect fluid. Even though things are happening inside the gas, the density at any point can be taken to be the same as it would be if it were measured at any other point. On top of that, if you were inside the container, the fluid would look the same and be measured to be the same in every direction. For example, if we wanted to know the mass density at this point, where there happens to be no molecule at this particular instant, we would obviously not say that the mass density was 0 at that point, even though strictly speaking it is. There's nothing there. We would probably consider some volume around the point so that it encompassed a large number of oxygen and nitrogen molecules, as well as anything else that might be there. And then we would take the mass enclosed in that volume, divided by the volume itself, to give us the average density at that point, and we'd call that the density at the point in the centre of the volume. The important thing would be that the size of the volume we took for the calculation would have to be large enough to give us a sensible measure of the average mass density for that point. We would need it to have encompassed enough oxygen, nitrogen and any other molecules so that we had a representative sample for that region, and yet we wouldn't want to make the sampling volume too large. Similarly, of course, if we chose a point where there happened to be a molecule, we wouldn't simply consider the actual molecule itself to get the mass density at that point. We'd do the same process of taking the mass enclosed by a large enough volume around it and then calculate the total mass over the total volume. And by doing that kind of thing at every point in the fluid, we could say that we could know the mass density at every point. And in this case, because the fluid as a whole is more or less at rest in a container which is also at rest, the mass density would be the same at every point, even though the molecules are moving. It is what we call a perfect fluid. In fact, Wikipedia defines a perfect fluid as a fluid that can be completely characterized by its rest frame mass density ρ and its isotopic pressure P. If you like, the mass density is the same at every point in this particular gas, measured on a large enough scale, and the pressure of the gas is the same everywhere as well. In order to have some understanding of the cosmological constant, then, we must first apply the idea of a perfect fluid to the whole of the universe, which of course is made up of massive galaxies which are enormous distances apart. We know also that there are clusters of galaxies and even superclusters, and in some parts of the universe there are immense voids or spaces of nothingness. Also, we would not simply want the mass density at each point, we would want to measure the mass energy density at every point in space, and clearly in order to think about the universe as some kind of perfect fluid, we would have to take incredibly large volumes around a point to get a fair measure of these densities at that point. The volume considered would have to be large enough to include galaxy clusters, superclusters, and voids, if it is to give the same answer at every point in the universe. Only then could we say that the universe could be represented by a perfect fluid. And that is the kind of assumption that we'll have to make about the universe, justified or not, if we want to express it, the whole of it, in terms of Einstein's field equations. We say then that the universe is taken to be homogeneous and isotropic, such that we're able to think in terms of knowing the 16 g mu nu values and the 16 t mu nu values at every point in the universe, and they will be the same at every point, according to this way of thinking, because we take the universe to be homogeneous on an extremely large scale. Clearly this means we will be ignoring what's going on in the universe, just as we were able to ignore the movement of oxygen and nitrogen molecules in the analogy about an enclosed gas such as air. The black holes, the galaxies in the universe, whatever they're up to, even on a fairly large scale, will be ignored, because our measurements of densities are taken by considering even larger, much larger volumes of space. In thinking about modelling the universe in this way, and in thinking therefore about the cosmological constant, we're not concerned with the fine detail of what's going on in the universe. However, there are two important questions that we must consider. Number one, is the universe itself spatially curved, either positively or negatively, or not at all? And secondly, is the universe expanding or contracting, or neither, just static? And by the first of these questions, we don't mean the kind of curvature of space-time that we've been considering around masses such as black holes and the like. We mean, does the space of the universe as a whole have curvature? And hopefully that idea will become clearer as we think more about it in a moment. By the second of these questions, we mean how or whether the universe as a whole is expanding, not just bits of it. In fact, you'll see it will not relate simply to the idea that the things in the universe are moving away from one another, but rather with the idea that space itself is expanding or contracting, and the things in it are simply being carried along by that expansion. So, given those two assumptions about being homogeneous and isotropic, how can we apply the bare Einstein equations to the whole of the universe? Well, in a way, there are two things that we need. We need to know something about the mass-energy side of things, not just mass, obviously. And also we need to know something about the geometry side of things. In other words, we need to know the stress-energy tensor, T mu nu, for this so-called perfect fluid of the universe. And we need to know a useful metric tensor, G mu nu, for it, one which will allow for the fact that the universe can expand and maybe even contract. But you may ask then, what about the R's, the Ricci tensor and the curvature scalar? Don't we need to know them also? Well, you should recall that the Ricci tensor R mu nu and the curvature scalar R are each made up exclusively of the metric tensor and its derivatives. So once we can find and write down a useful metric tensor, in a sense we've got the whole of this left-hand side covered. Let's look first then at the right-hand side of the equation, the stress-energy-momentum tensor side of things. Here's what we had for the general expression which described the 16 components of T mu nu when we discussed it in video number 18. It is, as you should recall, symmetric, and the colouring here is meant to help represent that. The three yellow entries labelled momentum density are identical to those labelled energy flux, all due to different ordering within a multiple differentiation. The same is true for the blue shear stress and momentum flux, and all these yellow and blue coefficients depend on some sort of sideways changes within what we might call the fluid of the universe. The diagonal terms, on the other hand, are much more direct. The purple T00 was clearly seen as the mass energy per unit volume, whereas the grey components, although seen as a momentum flux, had the momentum direction and any changes of it perpendicular to the surface through which the flux passes, in other words, pointing into it directly, and this could be interpreted as a simple outward pressure, the pressure of the gas or fluid from the moving objects. All of the mathematics of this has been well worked out for gases and liquids or whatever. For example, in the study of fluid mechanics, if the gas or liquid is in some kind of turbulent motion, then each one of these 16 components of the tensor would have some value which was different from zero, and they would probably be different from place to place within the fluid because of the turbulence. However, we're going to be thinking about a perfect fluid, and even though for a perfect fluid at rest there may be internal movement, a bit like we had with random movement of molecules in the analogy with air, such movement balances out in the sense that overall there's just as much sideways change in momentum in one direction as there is in the opposite direction. This all means that the form of the stress-energy tensor for a perfect fluid at rest is very much simplified, and it actually looks like this. You should notice here first that I've chosen to use the symbol epsilon for T00, the energy density, and I've used capital P for the pressure of the fluid. Often you'll see rho on its own, or sometimes rho c squared used for the energy density, and you will see a lowercase p for the pressure. I felt that epsilon better represents a more general energy density, which will essentially be the same as rho c squared if only mass is present, and I also felt that capital P can less easily be confused with rho when typed out. Anyway, here you can see that only the diagonals are non-zero and all the other components are zero. To put it crudely, you could say that from the random internal motion of the various objects, there is, on average, no sideways changes when thinking about momentum, And so a perfect fluid like this contains no sideways momentum flux and no shear stresses. Only the diagonals are populated in the stress-energy tensor of a perfect fluid. So in assuming that the universe can be considered to be a perfect fluid, we only have to consider the energy density and the overall pressure, the p-values here being the same as one another. You could crudely say that the values of force over area for the three directions in space are the same as one another. So this will be the form taken for the stress-energy tensor of our universe, and these values of epsilon and p will be considered to have the same value everywhere in the universe. Now, as an aside, even though we are missing out virtually all of the mathematics, it might be worth noticing here that what we might call the contraction or trace of this tensor, which is the sum of the diagonals, is this plus these three. And that expression, epsilon plus 3p, will come up again later in some of our formula. That's by the way. But at this point, we have what we can take as the stress-energy tensor for the whole of the universe, at least given the assumptions we're making. So we now have the right hand of Einstein's 16 field equations sorted if we want to consider the universe as a whole under the assumptions of homogeneity and isotropy. Now, what about the left-hand side? What about the metric tensor of this universe? Don't forget, we're not interested in the fine detail, the black holes, the stars and the galaxies. The metric must take the whole of the universe into account and have the same 16 values at every point in space. But also, crucially, it must describe the measurement of a universe which can be considered to be expanding or not, and to be spatially curved in some way or not. Well, without going into the reasoning, the metric that we take for this is known as the Friedmann Lemaître Robertson Walker metric, or the FLRW metric, and the space-time interval form of it can look like this. Now, if you look closely at this, you should be able to see that it is based on spherical polar coordinates. It has a spatial part to it with radius r and angles theta and phi, and it should also be obvious that we could write the metric tensor g mu nu from this space-time interval equation like this. And you can see here that the speed of light, c, in this has been set equal to 1. Now, as I say, we won't attempt to explain how this FLRW metric might be derived, but rather we'll try to discuss the various parts of it in order to see how it might meet our requirements. Remember, it must describe a possible expanding and a possible curved universe. I say try to discuss because there are different conventions for writing down this metric and for interpreting it. And a good course on cosmology would take some time to deal with that mathematics. But here we'll try to find a path through it which doesn't cut too many corners. And at least looking at it, you should notice the presence of two new variables in it, little a and little k, or rather the Greek letter kappa. One of these, a, relates to the possible expansion of the universe, and the other, kappa, relates to any spatial curvature that the universe might have. And so let's look in a very limited way at each one of these in turn. Little a can be thought of as the time-dependent expansion rate of the universe. And just as a reminder, we're talking about the expansion of space and not space-time for this discussion. In the limited way in which we will discuss it here, little a has no units and is simply a number which at any given time is the same everywhere in the universe, but it's a number which can potentially change with time. In some books, there are other ways of formulating the equations for the expanding universe where this a can have the units of distance and other things are adjusted accordingly, but in the following discussion, a is taken simply to be a multiplying factor which can change with time. And in order to help appreciate what's meant by this time-dependent expansion factor, we'll focus first on a two-dimensional space and then transfer the ideas to 3 dimensions. Consider then this illustration of a 2-dimensional space. As usual, the black border is simply to imply that we're looking at a limited region of the space, and the Cartesian type grid has been added here for convenience. You might loosely call it the fabric of space, onto which we can position things. It doesn't matter for this illustration whether the space is flat or curved. Let's suppose then that at this moment, right now, we have 2 galaxies somewhere in this region, say here and here. And let's suppose that they're only moving apart or towards one another extremely slowly within this space. Essentially, they are a fixed distance apart in the space because their movements are so ridiculously slow. We will call the time for this scenario t0. And let's suppose that we measure the distance apart of the galaxies at this time, and it's found to be d0. I've shown d0 here in red, and you can see that it has about 4 units on the background grid on this fabric of the space. Now let's suppose that the space itself expands and doubles in size, and suppose that it takes the galaxies with it, so that at some time t greater than t0, the situation looks like this. You should notice now that the galaxies are still separated by about 4 of what I've called grid lines, but those grid lines are somehow twice as far apart as before, which means that the actual separation of the galaxies has increased by a factor of 2 from what it was before. In this situation, the galaxies would actually be measured to have an increased new separation, even though they themselves have not actually moved within the space. Let's suppose that the new measurement of the separation is d, which is shown here now in blue. I should stress again, the galaxies have not moved further apart in the space, but rather they have moved with the expanding space. The 4 units of this grid could be said to be the co-moving distance between the pair of galaxies, and this has not changed during the expansion. It is constant for these galaxies, which, remember, we assumed are essentially stationary within the space. However, the galaxies have moved apart and will be measured to have moved apart because the space itself has expanded. The co-moving separation of these stationary galaxies remains constant, whether the space itself contracts or expands. These stationary galaxies will always be these 4 units apart in that sense, and yet the measurement of the separation changes. In this example, it has changed from the red d0 to the blue measurement d, and we could express this kind of thing using this formula: d equals a of t times d0, where a of t is the expansion coefficient at the time that the second measurement was made, at the time t. It is the multiplying factor at that time. Also, it should be fairly obvious that the expansion coefficient at time t0 must be 1, which means, trivially, that d0 is measured as d0. We're not thinking at this stage about what a will look like as a function of time. All we can say at the moment is that if the coefficient a is constant over time, then it must be constant at a value of 1, and we will have a static universe. When we do have a dynamic universe, which is either expanding or contracting, we will take the time t0 to be when a equals 1, and that is usually taken to be what we might call the now time. Expansion or contraction can take place in the past, when t is less than t0, or it can take place in the future, when t is greater than t0. Now, if we look at this FLRW metric again, we can see that the spatial part of it, which is essentially a particular form of spherical polar coordinates, is all multiplied by the expansion factor a squared, and that the time part of it is not. This coefficient a is concerned with the expansion of space as time passes, and is shown here as a squared, obviously simply because the formula for space-time interval deals with the squares of distances and times. This all means that the assumption is built into this metric that space can be expanding if A at a particular time is greater than 1, or contracting at those times when A happens to be less than 1. So, from what we've just discussed, we can immediately say that at time equal to t0, the now time, the metric must be given by this, where A has been made equal to 1 in these three positions in the metric tensor at time t0. Therefore, at this time of t0, we could say that apart from the kappa, or k, which we'll discuss in a moment, the spatial part of this metric essentially describes space being measured using spherical polar coordinates. If you need a reminder from video 6, the metric tensor of three-dimensional spherical polar coordinates was given by this. And this all means that at t0, the now time, we are measuring space essentially using spherical polar coordinates, apart, of course, from the extra kappa, which we'll get to in a moment. However, there are two important scenarios. Firstly, when there is no expansion and A is equal to 1 for all time, and secondly, when there is some kind of expansion which depends on time. So firstly, A is constant at a value of 1. Clearly, if there was no expansion or contraction over time, such that the expansion coefficient A was always equal to 1, we would have a static universe. Granted, the galaxies themselves may move around and change within the universe. Some of them could even come closer together or go further apart, but the grid lines of our illustration would remain fixed. The universe itself wouldn't stretch or contract, and so if the galaxies behaved a bit like the molecules in our earlier example, there would be no substantial change over time in how the universe looks in any particular direction. The universe would be static, and that would essentially give us the situation that the cosmologists of Einstein's day had assumed. The horizontal line graph, which we had earlier for the relative size of the universe, could equally well represent a graph of A against time if A is constant at a value of 1. Secondly, however, and much more importantly, we can consider a situation where the expansion coefficient A can change with time, and we will ensure for convenience that it has a value of 1 at the present time of t0 at the now time. Clearly, the details as to the way the expansion coefficient changes with the time will have a dramatic effect on the way the universe either expands or contracts, and we'll discuss more of that later. But I hope that you can now more or less understand what we mean by the expansion coefficient A in this Friedmann, Lemaître, Robertson, Walker metric. However, even if A were to be 1 for all time, with no expansion and a static universe, there's another extra factor in this metric which we need to think about, and that is the K or kappa here. This is a measure of the curvature of space, seen here in the metric measuring that curved space. On account of the spherical symmetry that we have in the coordinates of this metric, this curvature only affects the r dimension here and doesn't affect the other spatial dimensions theta and phi, and you can see that from the presence of kappa only in the radius term. Unlike the A coefficient, which expanded all of space and needed therefore to be multiplying all three spatial dimensions, this kappa need only distort, if I can use that word, the radial dimension in this particular set of spherically symmetric coordinates. It's important to realize, however, that this kappa is a different kind of measure of curvature than the Riemann, Ricci, or scalar curvatures for space-time. Each of these three R's is considered to measure some aspect of the curvature of an event in space-time, but the curvature kappa here is a measure simply of the curvature of space rather than space-time, and is itself a straightforward scalar, just a number. In fact, we will consider it to have only three possible values, +1, 0, and -1. Granted, that can be confusing without a full discussion and explanation, but that's only one possible confusion here. There are a few others, and as I say, they can only really be explained by going into the mathematics and conventions of all this. For instance, it would seem that for certain values of kappa and r, this whole term could be negative. And if we're dealing with this metric tensor in the usual way, that would ring alarm bells about the signature of the metric. We'd have two negative entries. Also, just in case you notice, it is conceivable, on the face of it, that this term could involve a singularity and the whole term could blow up. Now at this stage we don't need to explore those details, and you can read more on the mathematics of all this if you wish, or do a decent course, as I say, on cosmology. Our aim here is simply to try and see how this kind of metric can be used to explain the need for the existence of the cosmological constant in Einstein's equations without the need for the rigorous detail. So we'll ignore those confusing things, but we will, however, look at a few other things about this metric which stand out, things that we can more easily cope with at this stage, especially in relation to the values of this curvature coefficient, kappa. Let's look then at the three possibilities one at a time. First, kappa equal to 0. You should see from the form of the metric that if kappa is 0, this bracket in the denominator becomes 1. And so if we also for the moment assume a static universe and put the expansion coefficient a equal to 1, it means that the spatial part of this metric tensor becomes the same as the one we had for flat space when we were using spherical polar coordinates in video number 6, namely this. In other words, for this FLRW metric, when k is equal to 0, we must be dealing with flat space, whichever kind of coordinates we use. Some of the consequences of this flat space, if you recall, are that three angles of a triangle would add up to 180 degrees, and also that parallel lines would never meet. Here is a two-dimensional illustration of that showing Cartesian coordinates in the background. Remember, however, that this idea about triangles and parallel lines also applies to all three of the dimensions of space with this Friedmann, Lemaître, Robertson, Walker metric when kappa equals 0. Now granted, kappa only appeared in one of the dimensions, r, when using spherical polar coordinates, but you'll realise that the more usual three directions of space, x, y and z, will each be functions of r, and so that if kappa is 0, it means that this three-dimensional space is flat. The three angles of a triangle will add up to 180 degrees, and also parallel lines will never meet. Such a space is said to be flat. Secondly, what about if kappa is equal to +1? Well, in a case like that, we say that the space being measured has positive curvature, and this would mean that the angles of a triangle in this case would add up to greater than 180 degrees. It would also mean that parallel lines would converge. Here is a two-dimensional illustration of that, showing one example of a positively curved surface, the surface of a sphere. Travelling in a straight line on such a surface would usually take you right around the sphere and bring you back to the same point. You realise, I'm sure, that this idea also applies to three dimensions. So if k is positive, a triangle measured in a plane within three-dimensional space would have angles which would add up to greater than 180 degrees, and any lines which started off parallel in that space would eventually meet. It's even true to say that travelling away from a point in a straight line in such a three-dimensional, positively curved space will eventually bring you back to the same place if kappa is equal to +1. Such a space is said to be closed. And perhaps a hint as to why this is so is via the space-time interval formula for this metric. If we assume for the moment that time is constant, dt equals 0, in other words, we consider a particular instant, and if we ignore any expansion of the universe by putting a equal to 1, then we're looking here at a formula for the measured distance between 2 points in three-dimensional space, or what we used to call, when time was not involved, the arc length, ds, between 2 points. From this you can see that for kappa equal to +1, The way in which the measured value ds varies with r can be illustrated by this kind of formula, and as r becomes larger and larger, it reduces to this. This means that at large values of r, any change in s, the proper length, must be reflected in r, the measured length, by a much larger amount. Parallel lines are measured to get closer together. Thirdly, of course, we could consider the situation where kappa could be -1. And again, we put the expansion coefficient a equal to 1 in this metric in order to simplify things. In this case, the radial measurement is again curved, but in a different way. It means that the space being measured can be said to have a negative curvature, as illustrated here by this saddle shape for 2 dimensions. Here you have to try and imagine that this 2-dimensional space continues in all directions out to infinity. It's been put in a black frame for obvious reasons, and in this space the angles of a triangle will add up to less than 180 degrees, and parallel lines will diverge, as shown here for these 2 dimensions. Such a space is said to be open. Once again, however, you have to try and imagine this kind of shape, but in 3 dimensions, in which case a triangle measured in a plane within that 3-dimensional space would have 3 angles which would add up to less than 180 degrees, and any initially parallel lines would be measured to diverge. Travelling away from a point in a straight line in this 3-dimensional space where k is negative will certainly not bring you back to the same place. Again, you can sort of appreciate this using the same argument as before. You can say that at large values of r, any change in s, the proper length, must be reflected in r, the measured length, by a much larger amount. Parallel lines are measured to get further apart. Now, I'm conscious that this has not been a very rigorous explanation of things, and the arguments have not been very tight or wholly accurate. However, the basic discussion may hopefully be helpful. Again, if you want to understand things more clearly, a good course on cosmology would help. That said, we should now have enough appreciation to go on from this point to get some handle on the cosmological constant lambda. We have a metric that we might use for measuring a space-time where the space is possibly curved and the space is possibly expanding with time, the Friedmann, Lemaître, Robertson, Walker metric. It's shown here once again with the speed of light taken to be equal to 1. And looking at it, we can say that in terms of curvature, only the r measurement is affected. The time measurement's not been distorted or curved in any way. It is -1 or minus c squared, like the Minkowski metric for flat space-time. You can also see that the 2 angular measures, theta and phi, although they have to be multiplied by a squared, a time-dependent number, they've not really been distorted or curved. On the other hand, the radial component is not only multiplied by the number which is the square of the expansion coefficient a, it also has the kappa term included in the denominator, and that extra term allows for measuring a space which could be flat or curved, either positively or negatively, depending on the value of kappa. These are 2-dimensional illustration of that. This Friedmann, Lemaître, Robertson, Walker metric fits the bill for exactly what we want. We needed a metric that would allow for a spatially expanding or contracting universe, and we needed that metric also to allow for the space to be curved, or not, and by that we mean the whole of the space to be curved, right out to infinity. I should stress again, this kappa is not the curvature of space-time around a particular mass or region of energy, which is the kind of thing we've been thinking about with Einstein's field equations previously. It is the curvature of space, of the whole of the universe, on account of the mass energy within it. And as you'll see, it's to do with the ultimate fate of the universe. Okay, so now we have a number of useful things for thinking about the expansion of the universe. Firstly, we have the definitive set of equations derived by Einstein, his raw field equations. Secondly, we have a stress-energy tensor which can be applied to the whole universe under the assumption that the universe can be considered to be a perfect fluid. And thirdly, we have a metric tensor for the whole universe which can describe the possible expansion of space as time goes on, and can also describe a possible curvature of that space due to the mass of the whole universe. And don't forget, having the metric tensor, we therefore also have these, the Ricci tensor and the curvature scalar. They essentially contain derivatives of the metric tensor, and so we can say that we've got the whole thing covered. This means that if we were to take this Friedmann, Lemaître, Robertson, Walker metric and the stress-energy tensor T mu nu and substitute them both into the Beer-Einstein field equations, it would produce a set of 16, or rather 10, equations which would describe the universe as a whole, as it changes over time, and they would include the idea that the spatial part of the universe could be curved or flat, and that it could be expanding or static. These equations could then be manipulated to produce a further set of equations, which are sometimes known simply as the Friedman Equations. Now obviously in this one video we will not be going through the process of working through this, but the equations that are produced, although complex, can be looked at in a fairly crude way to gain some understanding, especially as to the history of the cosmological constant. In other words, why Einstein introduced it in the early 20th century, and also why it's needed today. The Friedman equations themselves can be rearranged in various ways by substituting a part of one equation into another and so on, giving a variety of ways of displaying what are still often simply called the Friedman equations. Perhaps the most useful pair of equations for us here are these, where epsilon, the mass-energy density of the universe, and P, the pressure of the universe, are shown in different colours in order to make them stand out. Looking at these equations, you should recognise that A dot is the rate of change of the expansion coefficient A with time, and A double dot is the rate of change of that rate of change with time. This means that we can operationalise, or if you like, think of these entries in the Friedman formulae as being a kind of normalised velocity and normalised acceleration of an expanding universe. They're not strictly that. In fact, the first of these terms is what is known as the Hubble parameter, sometimes called the Hubble constant. However, for our purposes, these expressions can in turn be thought of as representing the velocity at which the universe is expanding, if it is expanding, and the acceleration of that expansion, if there is one. Now, before we take a look at these Friedman equations, it's probably worth saying that something very close to these Einsteinian versions of them can fairly easily be derived using the Newtonian gravitation formulae. If you go through the mathematics using the basic Newtonian equations that we've considered in earlier videos, and it really is not difficult, they would give these two equations. The first thing to notice about these Newtonian versions of the equations is that the first one has a kappa in it, and yet there's no kappa in any of Newton's formulae. Where did it come from? How did it get there? From a Newtonian derivation? Well, it comes about, in this case, from the conservation of energy. In the Newtonian derivation, the energy must be conserved, and that constant amount is bundled together with other constants from Newton's equations and simply called kappa, a constant. The other thing perhaps to notice is that these Newtonian Friedman equations have rho, the mass density, instead of the energy and pressure terms epsilon and p. Understandably, there's also a c squared missing because the rho c squared would be the mass energy density. Anyway, we're not going to use these Newtonian versions, so let's go back to the Einsteinian ones, those that came from our model of the universe using the stress-energy tensor of a perfect fluid and the FLWR metric. And let's first of all look at the second of those equations relating to the acceleration of the universe. Even though Friedman's equations were not developed until the 1920s, you can probably appreciate from this particular equation why Einstein was shocked when he realized that his equations did not agree with the accepted idea of his day that the universe was static and unchanging. This Friedman equation demonstrates that very clearly for us. Epsilon, the constant energy density of the universe, is positive, as is P, the pressure in the universe. That means that this term on the left-hand side, which is some kind of representation of the acceleration of the universe, is constant, and the sign tells us that it is also negative. According therefore to Einstein's new equations, as demonstrated by these Friedman solutions, the universe cannot be static. There is some kind of negative acceleration, in other words, an acceleration inwards. His equations therefore don't seem to be in accord with what Einstein and others believed at the time to be reality, that the universe was static. His new theory may well have explained a number of other things, such as the bending of light by gravity and the orbit of the planet Mercury, but it appeared to have failed miserably on this important test for a static universe, which was thought by many at the time to be essential. Thinking at one level, simplistically, I suppose Einstein could have left his equations as they were without any extra term, and he could have suggested that the universe was temporarily static, so that the situation could be represented like this. If he'd proposed this, and I'm not suggesting that he did, he could have said that his equations were okay, because for this temporarily static universe there's a negative acceleration. In earlier times, t less than t0, the universe could be said to be expanding, but slowing down on account of the negative acceleration, and in future times, t greater than t0, it would be contracting faster and faster. He could have argued that at the current time, right now, the universe appears to be temporarily static. However, it wasn't as simple as that. It seems that there were philosophical and perhaps physical reasons why cosmologists believe that the universe has always looked the same as it does now. It was believed to be static at all times. Therefore, Einstein's equations should have predicted this kind of thing, where the relative size of the universe is unchanging at a value of 1. Going back to that Friedman equation which showed up the discrepancy for us, it may be easy to appreciate how Einstein tried to improve his equations in order to get what was thought at the time to be the right answer. The negative acceleration or contraction of the universe shown here in this equation could easily be gotten rid of by adding a constant positive term on the right-hand side of it, exactly equal to the size of the existing negative term. The acceleration that this equation, and therefore the Einstein equations, predicted would then be made equal to 0. As is often the case in physics, the constant was written down so that it included a mixture of other constants in order to make equations look neater elsewhere, and so it would be written in this Friedman equation as capital lambda c squared over 3, where lambda is some constant which has been chosen to get the right answer of 0 for this acceleration term. In other words, the value of lambda was essentially chosen by Einstein so that the positive term lambda c squared over 3 balanced out this negative term, making this acceleration equation equal to 0. Adding the term here, of course, in this Friedman equation meant that it also had to appear in earlier equations in the derivation of those of the Friedman equations. In other words, from Einstein's field equations, and so Einstein's field equations were modified from this to this. And this is how you'll often see those equations written when they are applied to the universe as a whole. Now, while all of this might look like a bit of a fudge, it did at least seem like an appropriate fudge, which made the equations fit what was believed to be reality, and so the pragmatist might have been comfortable with it, and assumed that some kind of explanation would be found for it at some future date. However, as you're probably aware, alongside those who argued for a static universe in Einstein's day, there were others who argued for a changing universe, and in the earliest 20th century experimental evidence was beginning to grow for that idea. Some years earlier, in 1912, Vespo Slipher had started it off when he made astronomical measurements which suggested that most spiral galaxies had sizable redshifts. In other words, they were measured to be receding from us at considerable velocities. Friedman's Equations, without the fudge factor, came along in 1922, suggesting that the universe could well be contracting in some way, or at least expanding less quickly. Later, in 1927, Lemaître gave strength to this kind of argument, suggesting that the very distant galaxies must be travelling faster away from us than the closer ones, and the relationship seemed to be linear. The velocity of recession seemed to be proportional to the distance away. A little time later, in 1929, Edwin Hubble used some of Slipher's measurements and many of his own from his observations to give strong evidence for a clear quantitative relationship between the velocities of various galaxies from their redshifts and their distance away from us. This is embodied in the Hubble law, which we would write nowadays as V equals h0d, where V is the receding velocity of the galaxy, d is the proper distance of the galaxy from us, and h0 is the Hubble parameter, at one time thought to be constant, but as we'll discuss in a moment is now believed to vary with time. Here is Hubble's famous straight line graph of V against d from his experimental work. So faced with the ever more popular idea that the universe was expanding, Einstein abandoned his cosmological constant in 1931 and reverted to the original versions of his equations without it. Einstein could then argue that his 16 or 10 field equations predict the original version of the Friedman Equations, one of which suggested that the acceleration of the expanding universe was negative and depended on the mass and energy, etc., within it. The model of the universe could then be taken to be any one of the three options which we discussed earlier. He could assume that the now time, or the t0, is somewhere, say, here, and the universe is expanding. Each of these curves shows a positive slope for the current time of t0, and this could be said to agree with the measurements made by Hubble at the time. The universe is expanding. There then could follow three possible scenarios. Either the universe started off with too little velocity for the mass energy in it, and is being pulled in much more strongly by that mass, thereby following the blue curve here, slowing down and then contracting to zero size. Or it started off with just the right velocity, a kind of escape velocity, so that the mass energy in it is slowing it down in such a way that it ends up eventually with zero velocity when everything is infinitely far away from everything else, as shown here by the purple curve. Or the universe started off with more than just the right velocity, over and above, if you like, the escape velocity, so that the mass energy is pulling it in and slowing it down, but only enough for it to end up with everything continuing to expand at some constant velocity forever. It seemed, therefore, from the 1930s right up to the 1990s, that Einstein's equations didn't need any cosmological constant, but ticked all the boxes for a theory to supersede that of Newton. However, in 1998, by observing the redshift of exploding white dwarf stars known as Type 1a supernovae, which could all be assumed to have the same inherent brightness, two independent groups of scientists showed that the universe was actually expanding at an ever-increasing rate. Instead of the expected straight-line relationship between velocity and distance for the galaxies which Hubble and others had found with the equipment they had, and the distances that they'd been able to explore, each of the two groups in 1998 obtained what amounted to a curved relationship, as illustrated here by the blue line on this graph. This unexpected result, the departure from what was thought to be a straight line, meant that not only was the universe expanding, but it was doing so at an accelerated rate. Galaxies were therefore moving away from one another faster and faster. Cosmologists in the period between the 1930s and the 1990s had expected that the velocity of recession would always be slowing down because of the gravitational attraction of all the mass and energy in the universe. The only real question for them was whether there was enough mass energy in the universe to pull it all back to a big crunch or not. If you like, we were believed to be probably somewhere here at T0. The universe was expanding, but on account of the gravitational attraction it was believed that the expansion rate must be decreasing, and the ultimate fate of the universe must be one of three things, as shown by these three curves, which were discussed earlier. That meant that in that period of time, from the 1930s to the 1990s, Einstein's original equations, without the cosmological constant, reigned supreme. What cosmologists now had to contend with after 1998 was that the ultimate fate of the universe seemed to be more like that shown by this black curve. It wasn't simply a case that mass and energy would be pulling the universe in, so that one of the other three scenarios would happen: big crunch, expansion to zero velocity, or expansion to fixed positive velocity, but rather that the separation velocity of things would continue to increase as time goes on. It's as though there is some kind of outward force pervading the universe, pushing everything apart and overcoming the attractive force of gravity from all the mass and energy in the universe. Now, in a sense, the idea of a force pushing out was exactly the kind of fudge that Einstein had introduced into his equations earlier in order to try and keep the universe static. The way in which we approached that idea was through the Friedman Equations, by adding something to the particular Friedman equation which describes what we might call the expansion acceleration. Einstein had added this term in order to stop this negative acceleration and to push back on the gravitational attraction outwards, but just by the right amount to keep things static, to make this acceleration zero. And that in turn, of course, meant that there had to be a similar term in his field equations, lambda g mu nu. Now that we know from 1998 that the expansion of the universe is actually accelerating, we need an even bigger term than Einstein had suggested, not simply to keep the universe static, but to make it accelerate apart. The extra term needs to overcome gravity and some. So, the cosmological constant lambda is back in, and is assumed to be bigger than what Einstein had originally suggested, big enough not only to overcome the pulling together of the universe, but also to bring about a resultant outward acceleration of that expansion. But what is it? What is lambda? What actually causes this anti-gravity type of effect and pushes the universe apart? Well, the way we've written it into Einstein's field equations, it appears on the left-hand side. It adds a positive contribution to the space-time distortion side of those equations. However, we could equally well have put it on the right-hand side, the mass-energy side, as a negative term, like this. And we could then, however, reconfigure the tensors and constants on the right-hand side so that the whole equation could be written like this. Now, think about this. If the stress energy tensor T mu nu can be thought of as the normal positive mass and energy thing that pulls things in, it would seem that this new addition, being negative, is a kind of negative mass energy, which must surely push things out. T mu nu is doing the attraction in the universe, and this term, this negative term, is doing the repulsion. And clearly most of the things that make up this term are givens, namely the various constants of nature and the metric tensor g mu nu from the FLWR metric. However, the value of the cosmological constant, the multiplier in this term, the lambda, effectively controls the strength of the repulsion and of the outward acceleration of the universe, and this is a constant which must be determined by experiment. But what makes lambda do what it does? We know about the positive T mu nu, which is all about mass, energy, momentum, pressure things, and we know that it does the pulling in. But what makes up this term? to do the pushing out? What actually causes it? Well, you will probably know that the name given to what causes this repulsion is dark energy, and it is currently believed to make up about 68% of the mass energy density of the universe, and yet it's some kind of mass energy which produces repulsion. The estimated density of dark energy throughout the universe is extremely small. In mass units, it's estimated to be about 7 times 10 to the minus 27 kilograms per cubic meter. But of course, it's in every cubic meter of space, and so there is a lot of it. And although the name dark energy has been coined for it, nobody really knows what it is. Perhaps the best and worst candidate for it is the quantum mechanical zero-point energy of space itself. Quantum mechanics predicts that there is energy in the nothingness of a vacuum as particles come into and out of existence. However, if you use quantum field theory, which is one of the most successful physics theories in other areas, if you use that to try and calculate a value for the energy density of the vacuum of space, it produces a result which is many, many orders of magnitude too large to be equal to the density of dark energy, which accounts for the observed acceleration. That figure of 7 times 10 to the minus 27 kilogram per cubic meter. The figure from quantum field theory is up to 10 to the 120 times bigger than this, and if it were real, would mean that the early universe would have such a big cosmological constant that it would have expanded so quickly and dramatically that no stars and galaxies would ever have formed. This cosmological constant problem, as it's been called, is one of the current outstanding problems in physics and has been called the worst theoretical prediction in the history of physics. Now, before we finish this series of videos, perhaps we should just mention the idea of the cosmic horizon. It seems possible that the universe is infinite in its extent, even though we can only see a small fraction of it. This limit of our observation is known as the cosmological horizon, and depending on exactly how you define it, you can explain it in a variety of ways. Here is a much simplified explanation. If the universe is expanding, and it is, and if that expansion is at a faster rate the further away the galaxies are, and it is, and if the expansion rate of the universe is increasing everywhere, and it is, then given the likely size of the universe, it is reasonable to assume that there are distant galaxies moving away from us at speeds greater than the speed of light. Now, this of course does not mean that they are travelling within space at those kinds of speeds, but rather that space itself in that region is expanding away from us at those speeds greater than the speed of light. This would not violate the laws of physics and relativity. The fabric of space itself can expand at speeds greater than the speed of light. It's the matter within space that is restrained to have subluminal velocities. It should seem reasonable, therefore, that there will come a time when the light from those galaxies, which are travelling away from us at speeds greater than the speed of light, will not be able to reach us here on Earth, and so we will not be able to see them. They will be beyond our cosmic horizon. And as time goes on, if the Earth was still around, then stars in the night sky would only consist of those in our galaxy, or perhaps some of our closest neighbouring galaxies. All the other galaxies will be beyond our cosmic horizon. And it's interesting to wonder what kind of theories physicists and mathematicians would have come up with for that kind of observed universe, if that was all the universe they had to go on. So that's it. The aim of this series of videos, all 20 of them, was to try and fathom out how and why we moved from this to this, and from this very successful theory of gravitation to this one, with or without the cosmological constant. In the process, it is hoped that you've become familiar with some of the language of general relativity, and that you now have a reasonable understanding of Einstein's field equations, so that not only is the immensity of the physics and mathematics realized, but also something of the complexity and wonder of the universe appreciated. Hopefully then, if all this has been reasonably well understood, we can now be a little more confident in exploring some of the current ideas in cosmology, but that's for another day.